At first glance, this seems like it should be straightforward. The numerator goes to infinity and the denominator goes to infinity, so you could reasonably think that L'Hopital's rule is the tool that we need. But there's a problem. L'Hopital's rule is a statement about the limit of functions, not sequences. So it doesn't apply here. Now, in previous lectures, we've seen some connections between the limits of functions and the limits of sequences. Well, in this lecture, we're going to make that concrete in a way that will help us define limits like this one using the tools that we already have for the limits of functions. There's a lot going on here, right? So let's step back and look at all the pieces. The theorem starts out saying, suppose we have a function, and that it's defined for every value of x greater than some number. Now, suppose we create a sequence based on this function by defining the nth term of the sequence to be the value of the function at n. That's this part here. Then, once we've done this, then the theorem is saying that if the function has a limit at infinity, then the sequence also has to have the same limit. In other words, if we have a function whose limit at infinity exists, and we create a sequence by pulling values from that function, then the sequence is going to have the same limit as the original function. And the proof of this is relatively straightforward, so I'm going to leave that as an exercise in the online classroom. So now we can answer this question, right? Define a function, f of x, to be equal to the natural log of x divided by x, right? Then for x greater than or equal to 1, a sub n is equal to f of n, where a sub n are the terms of our sequence here, right? So what the theorem tells us now is that the limit as n goes to infinity of the sequence, the log of n over n, is equal to the limit as n goes to infinity of the log of x over x. Now we're not talking about a sequence anymore. Now we're talking about a function. So L'Hopital's rule does apply. And if we differentiate, the limit stays the same. The limit as x goes to infinity, and I should have switched. That should be an x there, not an n. The limit as x goes to infinity of 1 over x divided by 1, and this is going to be 0. Right? So there's our result. That is the limit of the original, that's the original limit, right? The limit of the sequence. So this theorem gives us a way to talk about a function of a sequence. Right, so again, let's kind of pull apart the pieces here. It starts with a sequence, and we know that this sequence converges to some number L. Then it introduces a function, and it builds a new sequence by taking that function of every value in the original sequence. Now, if the function is continuous at this value L, then the limit of the new sequence is equal to the value of the function at the original limit. So to see what this is saying, take a look at the sequence below here, which approaches 0 as n goes to infinity. Now, let f of x equal x squared plus 1. If we take every value of the original sequence, we can generate a new sequence by calculating f of a sub n. Right? And if we do that, we get something like this. Now, since f of x is continuous at 0, right? 0 was the limit of the original sequence. Then the limit of the new sequence, the limit as n goes to infinity of f of a sub n must be f of 0, which equals 1. And that does appear to be the value that the sequence is approaching. So essentially what this theorem is doing is it's saying if we have a function of a sequence and that new sequence is continuous at the limit of the original one, then we can kind of slip the limit inside of the function and calculate the new limit. Right, so let's look at an example. So what we have here is a sequence that's made by taking a function, cosine, of another sequence. The sequence a sub n equals 1 over n. So to start, we already know that as n goes to infinity, 1 over n goes to 0. And we know that the cosine function is continuous at 0. So all the requirements of the theorem have been met. So what the theorem tells us now is that this limit is the same as the cosine of the limit as n goes to infinity of 1 over n. We know what that limit is. It's 0. So this limit is the cosine of 0, which is 1. See, hopefully you see what I'm saying here about the limit, right? Because the cosine is continuous everywhere, but specifically it's continuous here. I could take that limit, slip it inside the cosine, and get the limit of the original function that way. So in the next lecture, we're going to kind of continue developing these analogs between what we know about functions and what we'd like to know about sequences by coming up with a version of the squeeze theorem or the sandwich theorem that applies to limits of sequences.